Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are moving to the next topic of the atomic physics, which is the Bohr model of the atom. We already studied this Bohr model of the atom topic in the previous lesson. We are doing the atomic spectra. That only the overview of that, and today we are doing the all the things related to the Bohr model of the atom, about the shells and about the electron orbits and all the things we cover, and we more focus on the thing which is called the energy transitions, and all thing involved with the Bohr model of the atom. So let's start with that, with the how it start. So in 1913, Bohr published a paper suggesting a very radical changes to a Rutherford planetary model of the atom. Bohr opposed the following. So these are some changes they do in the Rutherford model. What are those? So electrons can only orbit a specific distance from the nucleus. As Rutherford mentioned that the electrons are orbit the nucleus, but the Bohr also states that they are at the specific distance where they do the orbiting. So their orbitals are the quantized. The quantum model of the atom is again other model of atom. We discussed in the in the next lesson. But for now, you have to say that the orbits are quantized, and the total energy of an electron is governed by the distance from the nucleus. This basically they say is that the electrons which are orbit the nucleus, they are at some specific distance. The energy of the an electron is also quantized. Each orbit corresponds to particular energy level. They have some particular energy levels. Let's write over there. Like over there, we have a nucleus, and at the specific energy levels, they do the orbition like this. We all discussed this in chemistry too, in the grade 11 chemistry, that electrons have their specific levels of the energy level shells. Electron can only move between the energy levels by either absorbing or emitting the photon. Photon is the thing we again coming in this unit too. But the electrons are only moving in the specific between the energy level by the either absorbing or emitting a photon. The energy of the photon absorbed or emitted must equal the energy difference between the two energy levels. So energy of the which is absorbed or emitted, which have the equal difference between the total energy levels, all the orbits we mentioned. The electron that remains in a same energy level does not make the energy and is in a stationary state. So firstly, they start with stationary state and we go with the some levels of the energy. We discuss the levels basically, so it looked like that. So that's the thing, that levels we can discuss in this. So this has a first level, n is equal to 1, n is equal to 2, 3, 4, 5, and the infinity. That all have some EV charge on it, some EV energy on it, you can say. So that things which have, so label that things, and we have that. The Bohr's model lowest possible orbit is n1, n is equal to 1. This is the lowest energy level state of the Bohr model. And this state is also known as the unexcited or a ground state and the most stable orbit. This orbit has the always this charge, always this energy. All other orbits n is equal to 2, 3 or 4 and infinity are called the excited states and are not stable. So n1 is always the stable or the stationary state, and all of the them infinity till infinity are the excited state or the unstable states, and they have a different energies. Electrons will transfer between these states either by absorbing or emitting the photon or appropriate energy. So you can go from like n1 to n3, you can go from n4 to n1. These all are the transitions. These are called the energy transitions, and the energy transitions can be done by the absorbing or emitting the photon. That thing we discuss later on in this lesson too, that how when they absorb and when they emit and when they do the lower to higher transition, we do the higher to lower transition. These all things we discuss too. But for now, we have to just say that these are doing in that and Bohr model of the atom. When an electron goes beyond the n is equal to infinity, if they go from like n1 to n infinity, when they go beyond of this, so they leaves the atom, which ionize the atom with the kinetic energy. The minimum energy to remove an electron from the atom. This is called the minimum energy to remove the electron from the atom after the infinity. After infinity, they free the atom. They free the atom from after the infinity. They are not in that state anymore. to get the n is equal to infinity, and this thing we call as the ionization energy. That ionization energy in that particular in the ionization energy state, we have that kinetic energy is greater than zero, and that thing we sometimes have to find in that. We discuss these things in the like in practice questions too, that we have a questions related to this which we have to discuss. So for this we have to just know about that things. And the next thing we have, the electrons which orbit the nucleus are held in place by the attraction of the electric force. They do some electric force in that when they do orbit the nucleus. Between the protons in the nucleus and orbiting the electron, the electric force provides the centripetal force on the electron. They also provide some centripetal force on the electron. So we have a centripetal force is equal to the electric force, and we have centripetal force mv square upon r is equal to, we have this kq square because we have a same charges, we take as kq as square and we have r square. This formula is just for your knowledge. You don't have to be worried about this formula. You can't use this formula. We just do some these things and we have some formulas for related to that. For that, we have just I just tell you about the what is going on, what is going in the Bohr model, where if they mention that they orbit the nucleus with the attraction of the electric force. Again, we have electric force which provide the centripetal force on the electron. So that's the same thing we discussed in the other models. The main thing we have to discuss is the energy transitions and the line spectra. So we discuss the line spectra. Basically, we are more focused on the absorption and the emission spectra, and energy transitions can be happen with that. What they do. So the Bohr's models was able to explain why absorption and emission line spectra occur for the hydrogen and the other elements. So the absorption and the emission line spectra is more focused on the hydrogen and the other elements. We discuss how they absorb and how they emission the line spectra and why they do that. When high voltage is applied to the hydrogen gas, we more focus on the hydrogen gas in the cathode ray tube. When there is a high voltage applied to hydrogen gas and we have a cathode ray tube, a current is created in a tube. So in the tube, in the cathode ray tube, there is a current involving now. So electrons from the current collide with the electrons in the hydrogen atom, exciting them to higher energy levels. So what they do, they have some stationary state first. When the current will carry with the electrons, they will collide with that electrons. When they collide with those electrons with the hydrogen atoms, they excite them. They excite them to go to higher states, from the lower to higher states. So that thing from higher to lower states are doing with that thing, which is called energy transitions. And as the high energy levels are unstable, we know that these are the unstable things, they are not very stable. The electrons in the hydrogen atom eventually make their way back to the ground state. Sometimes, when they go to the high energy levels, which are unstable, so again they come back to a ground state, which is called from the higher to lower state. In this, we discuss they go from the lower, which is stationary, to the higher states, which are the unstable states. But sometimes they are unstable, because of that they come again from higher to the lower state again. So that at that time they losing the energy in the form of photon and they will absorb the electromagnetic radiations. So when they come again from the higher to lower, they will lose some energy. This is the important point you have to know in this. Bohr was able to show that each bright line absorbed on the emission spectrum corresponds to a unique energy transition between the energy levels. So we have some transitions, we have two types of transitions, and we have to know about these transitions now. So Bohr also rationalized that the gases absorb the same frequency of the electromagnetic radiations that they emit. For example, Bohr knew that when an electron in a hydrogen atom transitions from an 4 to 2, so from the higher to the lower, it emitted the proton correspond to a green light with 2.56 eV. That all are the calculations things. That now for 2 to 4, this absorb the photon. That all called calculation what we did in example 2. But you have to know these 2 points now. What are those points? Your delta E. We discussed delta E in this. So delta E is if photon has if delta is positive. If delta is positive and the photon has been absorbed in that case photon has been absorbed, which means transitions go from the lower to the higher energy level. Like we go from 1 to 4, we go from 2 to 3. These are all the like lower to higher when the delta is positive and photon has been absorbed. When delta is negative and photon has been emitted, transitions from the higher energy to a lower energy level. Now the photon has been emitted. By this thing, when they emit it and they have a negative thing, so they're from like 4 to 3, they go from 4 to 1, 2 to 1, that thing, they do it from higher to lower, from to the ground state. So, what is the delta E? Delta E is given us over there. If we have to find the energy of photon, we use absolute delta E. Absolute delta means the energy of the like final energy level to the niche minus the initial finalization level. So this is basically that F or I means if like you go from uh, N to wait, like if you go from the N2 to N4. So this N2 is your like, so when you write this as a delta E, so you write it as the E4 minus E2 like this. This is equal to the delta E or the energy of the photon. That we all discuss when we do example now. So that's the 2 points we have to discuss. These are the very important points, that when this positive, absorb the photon and lower to higher transition. Negative, we have emitted the photon and the higher to the low energy level transition. That's the important thing. And we have one more formula in this. If you have to find any energy of the nth orbital, if you have a like one orbital, we have a fourth orbital, we have a fifth orbital. To find this in joules or EV, you can use this formula. E1, which is a ground state, energy is always be this minus 13.6 EV is always this for n is equal to 1. You take this thing, divide this by the principal quantum number, that whenever that if you have to find for the fifth, if you have to find the energy for the fifth orbital, so you can use this formula like F5 is equal to minus 13.6 EV divided by the 5. You get something which is your energy of the fifth orbital in EV. Or you want for joules, so you can convert this to joules. So that's the formula we also used. And before doing that example, we have some limitations. Limitations of the Bohr models, which can't be like explained by them. So what it does, it could not explain the spectra of some more complex atoms. More complex atoms, which atoms that had the 2 or more electrons. They didn't like explain that spectral thing. You could not explain why orbits were quantized. They mentioned that orbits are quantized, but why? These all things we discuss in the quantum model of the atom. But we cannot do like more in the quantum model of the atom, because this is not the thing we discuss more in this. This is for the higher studies, not for grade 12. It could not explain why electrons do not emit the electromagnetic radiations as predicted by the Maxwell. Electrons will undergo circular motion in the Bohr's model. Why they are not emitted by the electromagnetic radiations, this can't be explained by the Bohr. It could not explain why some spectral light split unicellular components in the presence of the static magnetic field. So this is again some Zeeman effect they mention, and they didn't like explain that thing, why the spectral light split unicellular components. So these are some limitations. You have to know some limitations, but again you can't get like a direct question from there, like write the limitation of Bohr model, but you have to know. And the theory we done so far in this Bohr model of the atom, you all know have to do this. Okay, we have some example. We have one example in this, that how can we deal with these sort of questions. So over there we have energy level. We have all energy level diagram over there till 1 to 6. We have determined the wavelength of the photon associated with an electron that moves between the following energy levels. State whether the lines, whether this movement is explained by the photon absorption or the photon emission. Okay, so we have to do this question, and we have first thing we have to find the wavelength if we go from like 5 to 2. Done. So if we go from 5 to 2, so how can we deal with this? So we do A first. So at E5, we have energy given to us. We have energy given to us which is minus 2.00 eV. We have energy at 2 which is minus 13.0 eV. We have to find delta E first. So we do final minus initial, which is 2 minus 5. So we have minus 13.0 minus 2.00 eV. This is also eV. When you calculate this, you get your delta E of about minus 11.0 EV. You get delta EV. And but this is the absolute one, so which means your delta E is 11.0 EV. Not in negative, you get the absolute thing in this. So we have to find the wavelength. You know that this thing is equal to hc upon wavelength. So you can find the wavelength from here, you know the energy. So wavelength is equal to h you have given to you. So you have to use the h for the EV thing. So we have 4.414 into 10 raised to minus 15 EV dot second, 33.0 10 raised to power 8 meter per second. We use the same formulas. Divide this by the 11.0 EV. When you put the things, you will get about 112.7. Then at the end, you can convert this into nanometers. So this is in nanometers now, and this is like the emission thing. This emit the thing because this go from like 2 to 5, which is all the emission. Next we have from 1 to 4. So again you have to do same thing. So I do the direct now. So A second for delta E, you have to find like go from like 4 to 1. They go from 1 to 4, but you have to do like E4 minus E1. You have E4 of about minus 4.00 EV minus 20.0 EV, which is a E1. So you get the absolute thing and you get the answer of about 16.0 EV, which is in positive because of the absolute. You again use this same formula. Now the wavelength is with C upon E. So 4.14 into 10 raised to power minus 15 EV dot second. 3.0 10 raised to power 8 meter per second. Divide this by the 16.0 EV. You have to convert this into nanos. So 7.4 nanometers. You know how to convert this, so I left it for you. And this is the absorption. So these are the two answers for the first A part. And we done this. For the second part, the maximum frequency of the light that would be absorbed by an electron in a ground state of the atom if a 15.0 eV particle passes by and collides with the electron. So they mentioned that we have to find the maximum frequencies which is absorbed by the ground state if the 15.0 eV is enabling that. Okay. So if we go from like electron can only jump to level equivalent by the less than equal to 15 point greater than equal to 15.0 eV. So from 1 to 2 we have a, so from here, if you do from here, so 1 to 2, if you find like the delta E from here, you will get like this is 7 eV. From 1 to 3, from like 1 to 3, you will get 14 eV. From 1 to 4, you will get a 16 eV. So there is something between the N3 to the N4. So the largest possible absorption is to from the N is to N3, which is 14 eV. So what you have to find now for B. So there means that the largest possible absorption is at N is equal to 3, where we require 14 eV. You know E is equal to H times F. So you have to find the frequency, which is E upon H. But you don't know the E in that case. But you have to find the E now. Your EV should be converted into joules now. So the 14 EV, you multiply this by 1.6 into 10 raised to minus 19 joules. You will get 2.24 into 10 raised to minus 18 joules. Because we want this in joules to put this in that E thing. So we put the things now, minus 18 joules divided by 6.63 into 10 raised to power minus 34 joules per second. When you solve this, you get 3.38 into 10 raised to power 15 Hertz frequency. So that type of questions are they need some thinking about that you have to do something like this to get the answer. We discuss this more some type of things in then when we do in the practice notes of this part, which is very important, and you have to watch this too because this topic is very important and you have to know that how that which type of questions you get in that. So for this, we completed the Bohr model of the atom too. So this is the Bohr model, and in the next lesson we're doing the last model, which is a quantum model of the atom. We have to just know some definitions and all, and we'll do some calculation work in that. So that's all for this lesson. I miss if I do vibe learns but not harder. Please like, share, and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till let's get it with Edu Vibe.